Hello, my name is Dr. Hammad Haider and you are watching sqadia.com. Today, my lecture would be on third week of development. And what I will be covering this lecture, this is the lecture outline. I will be covering the most important event of the third week, which is gastrulation or formation of trilaminar germ disc. We discussed in the previous lecture how the inner cell mass, which was surrounded by trophoblast, divided into two layers, which was the hypoblast and epiblast. Today in this lecture, we'll discuss how these cells, the epiblastic cells, migrate to form a three-layer structure, which is called as gastrulation or formation of trilaminar germ disc, and how the epiblastic cells migrate to form ectoderm, mesoderm, and endoderm. We will also be discussing formation of primitive node and primitive streak and how the cranial caudal axes are established. We'll be discussing formation of notochord. First, we'll be going through the formation of a notochordal plate, then how this goes into a notochordal canal, and why this is important for the neurulation to occur later on. I will be discussing neurulation in my next lecture, which will be during the period of embryogenesis. I will be discussing how the establishment of body axis and intraembryonic mesoderm takes place, or the right, left, dorsal, ventral, and cranial caudal axes are determined. How the formation of primary and secondary villi and definite placental villus is formed, or formation of Allantois takes place in humans, and what are the rudimentary structures which are formed from the Allantois. Congenital abnormalities during the third week of development. I will be specifically touching on the sacrococcygeal teratomas. Now, coming to the gastrulation. So what is gastrulation? Gastrulation is actually formation of trilaminar germ discs from bilaminar germ discs. We discussed previously that there were two main layers. There was inner cell mass and trophoblast. It was called week of tubes because it divided trophoblast into two layers, syncytial and cytotrophoblasts, while inner layer cell mass, which will be forming the embryo proper, divided into epiblast and hypoblast. Now this epiblast layer is actually lying on the top and hypoblast layer is lying in the bottom. Now they are sandwiched together. Epiblastic cell starts to migrate inward and invaginate into the hypoblast layer. Now their migration results in formation of three layers from two layers. The upper layer, which is called as the ectoderm, middle layer is called as the mesoderm, and lowermost layer, which is just lying superior or dorsal to the hypoblast, is termed as endoderm. Bilaminar embryonic germ disc is converted into trilaminar embryonic germ disc. Extensive cell shape changes occur, rearrangement, movement, and changes in adhesive properties as well. First sign of gastrulation is the formation of primitive streak. Due to proliferation of epiblastic cells, a linear thickening will be developed in the mid on the dorsal aspect of the embryonic discs in the caudal part. This is the beginning of development of primitive streak. Epiblastic cells proliferate and invaginate inside between the epiblastic and hypoblastic layers to form three layers, which is ectoderm, mesoderm, and endoderm. Now, before I've already told you previously in the previous lectures as well that it's not that one thing happens and ends and then the next thing starts. To make it easy and to make it easy to understand for everybody, we have divided this into different parts, but actually everything is happening side by side. When primitive node starts to appear, the same time the cell starts to migrate as well, and then from primitive node a streak lines appear, which is termed as primitive streak. By the time primitive streak has formed, cells have started to migrate and invaginate inward. Now this is the diagram. Now if you see this was the epiblastic layer and hypoblastic. Now by this time there was initially the two layers. As I told you, they are sandwiched together, but as cells starts to migrate, they become more and more apart from each other. So this is the epiblast and this is the hypoblast, the bilaminar germ disc. Gradually, the cells over here, which is on the caudal part, they starts to dip inward, and their dipping results in a specific formation of primitive streak. Primitive streak, and then this is formed. This is termed as primitive pit, a primitive node, As you can appreciate over here by the arrows, the diagram, the cells are going in. As they go from epiblast, which is lying more dorsally and on the top, they go down towards the hypoblast. As they migrate, the outermost layer will be forming the definitive ectoderm. The cells which come to lie in between form the mesoderm, and cells which come to lie close to the hypoplastic layer will form the endoderm. But all three layers, the ectoderm, endoderm, and mesoderm, all are formed from the epiblast, not from the hypoblast. So now this is another diagram. Actually, this is showing a cross section. They've taken one vertical and one horizontal cross section. This is at this and at this level. If you see this, now this was, I told you, this bilaminar germ, it is called as disc because it's a bit disc shape. It is an elongated disc shape in which this end, which is more convex, appears to be the cranial end, and with a shallow caudal port. Now, as this primitive node has formed, this will result in formation of primitive streak, and later on go towards this. Now, this is the cranial end, this is the caudal end. Now, this is the amniotic cavity, and this is the yolk sac. If you see it, this is the enlarged view of the same thing. This is where the cell starts to form. This is the primitive node, and this is the epiplastic layer. This is how the epiplastic cell starts to invaginate and migrate into the hypoblast. As hypoblast lying below and epiblast on the top, so cell starts to dive down into the hypoblast. Now this is, as you can see, appreciate the formation of primitive streak. Now, as it starts, this is primitive streak, which is one primitive node. Then cells will also migrate more cranially, which is towards the, at number 5 you can see is the precaudal plate, which will form on the later on the oropharyngeal membrane. This is the cephalic end, the archocephalic pole. This is the caudal pole. This is the amniotic membrane or amniotic cavity. You can appreciate this is yolk sac around it, and this is the hypoblast layer in which the cells of the epiblast are actually migrating in. So this is another diagram showing the same process but in a very different. Now instead of having a vertical and horizontal cross section, a transverse section has been taken up. And if you appreciate, this is the dorsal surface, this is the cranial end, and towards you would be the caudal end. A cross section has been taken, and this was the epiblastic layer, and this is the yellow is the hypoplastic layer. The cells in the center, they initially form primitive node. From primitive node they start forming primitive streak. As the primitive streak is formed, it migrates and the cell starts to invaginate inwards as they gradually migrate towards the hypoblast and come to lie in between. As they start to come to lie in between, the outermost layer becomes the ectoderm now, which includes the hypoplastic layer. The middle one layer becomes the mesoderm, and the innermost layer, which is just near to the hypoblast, becomes the endoderm. So, formation of primitive node. Primitive streaks develop into the caudal 1/3 of the embryo. Now remember this is very important, because if there is a abnormality in development of primitive streak, this will result in another entity called a sacrococcygeal teratoma. But remember that this will be the forming the 1/3 caudal portion, not the cranial portion. The cranial 2/3 will be from other cells. Epiblastic cells proliferate continuously and then are moving inward and increasing number in the midline. As I have told you, this becomes the midline now. This is the cranial mode. They continue to proliferate, they continue to migrate in. So cells are dividing and increasing in number. They're diving down into the hypoblast layer as well, and they're also elongating over towards the cranially. So the primitive nodes form from the caudal end. Primitive streak stretches and crosses towards the cranial end. So there is elongation from caudal to the cranial end. The collection of epiplastic cells which change their shape from columnar to polygonal cells are called as mesenchymal cells, and they are collected at the cranial end of the primitive streak called as a primitive node. Remember, now they start primitive streak, eventually a node. Why this is called a primitive node? Because here the cell starts to proliferate so much, they actually form a bump or a raised part over the amniotic on the over the layer of the epiblast, and on electron micrographs they appear as a primitive or node-like structure or a elevated bump-like structure, which was discovered by Hansen. So the moving surfaces of the cell first pile up to form a primitive bump known as the node. The node was first discovered in mammals by Hansen and is appropriately called as Hansen node in rabbits and other organisms, but in only humans it is usually referred to as primitive node. So up till now there is a primitive streak formation which occurs in the midline. It gradually extends from caudal to the cranial end, and at the cranial end there is a formation of a node called as primitive node. Once that is done, after that there is they continue. By this time the epiblastic cells are continuously proliferating and diving in or invaginating into the hypoblastic layer, forming the three layers, which is the ectoderm, mesoderm, and the endoderm. This is the diagram as well. You can appreciate how right over here. Now this is another cut section. It's a bit at advanced stage. Now this is the primitive streak. This at this level would be the primitive node. Now this is the primitive streak, and as you can appreciate the epiblastic cells have invaginated in, as they can be appreciated diving down. Those who have dived down, they form a new layer which is termed as mesoderm. This yellow portion is the hypoblast, and those which dive down near to the hypoblast we form the endoderm. Here as you can appreciate it's written endodermal and notochordal cells. Why? Now from where these notochordal cells came in, when we were discussing the formation of notochordal plate and notochordal canal, we will be again coming to this point that how this invagination has actually occurred first. But at this time we are only discussing primitive node, primitive streak, and gastrulation. This is the diagram. This is another diagram of primitive node, primitive streak, and the process of gastrulation. Now there are two diagrams. If you see, one is a dorsal view and other is a cross section. So dorsal view on the ACE diagram, you can appreciate how it looks like from the top. While in the diagram number B, you can see how even a cross section looks like. So if you see this clearly, this is the primitive pit, and this is a primitive node, and this is a primitive groove and a streak. So what actually happens is, why it is called as primitive pit is this is the point where it all starts. This is lying towards the 1/3 of the caudal region, but at this is the point when the cell suddenly starts to migrate and they dive down. If this is the surface, then suddenly when cells migrate down, there will be a pit formation. Now this is the point at which initially the process of gastrulation starts from this point. As you can see when you see it on one time, it will look like only a pit. Once you see it after some time, then you can appreciate a formation of primitive streak, as the cells are continuously dividing at this level and diving down and invaginating into the epiblast towards the hypoblast. So there is a primitive streak formation. Gradually these cells become so much, and then diving results in a formation of primitive groove. It's just like that a line appears, then there's a cells gradually increase in number and form a formation of a groove-like structure, which is termed a primitive groove. But at this end, when these cells are migrating from caudal to cranial end, on the primitive node, why it is called as primitive node? Because after once the primitive streak and groove has been formed, the cell at the point where the primitive pit was formed initially then again starts to migrate, and instead of this time invaginating in, they start to migrate and form a bump like structure which is called as primitive node. And this is the cranial end, this is the caudal end, and migration will take place from caudal to cranial side. As you can appreciate, this is the ectoderm now, which is the epiblastic layer, which is after invagination has become the outermost layer and is now called the ectoderm. This is the precaudal plate. This is the cut edge of the amnion, while this is the connecting stalk. And if you this is the dorsal view, so that yolk sac will be below this. Now this is the same view at this level. If you cut this embryo at this level, this is exactly how it appears. You can appreciate this is the primitive node and pit area. This is now, instead of becoming a streak, it has become a groove-like structure. The cells have become numerous enough to appear like a groove. This is the primitive groove. Now this is the ectoderm now, which is the embryonic ectoderm. Why it is called embryonic ectoderm? Because it was initially the inner cell mass which became the epiblast and hypoblast. Then migration resulted in formation of embryonic tissue, which was the ectoderm, because that was the inner cell mass will give rise to the embryo proper. Now this is the cuttage amnion. This is where the amniotic membrane comes in. Now this is the area. Now this is the hypoblast, and this area is the yolk sac. But between this hypoblast and epiblast, which was initially sandwiched together, now there is a lot of space. Why? Because epiblastic cells were migrated in to form another mesoblast or mesodermal tissue, which will eventually give rise to all the three parts of the mesoderm, which is the paraxial, intermediate, and lateral plate mesoderm. I will be discussing in details all these three parts and how they give rise to different structures when I will be discussing neurulation in the next lecture. So what is the role of primitive streak? There are few functions of primitive streak. Development of axis is actually, this is the point which determines what is the craniocaudal axis, what is the right left axis, and dorsal ventral axis. So development of primitive streak is responsible for identification of axis of the embryo, that one is can be identified. So craniocaudal means, if you see this diagram again, this was the primitive streak and groove formation. So this is the central formation of the axis. We know the cell will migrate towards the cranial pole. So this becomes the cranial pole and this becomes the caudal pole. Now this is the dorsal side, and then if you see this end cut section, this becomes the dorsal side, this becomes the ventral side. And this also determines the right and left side. Usually this is the right side and this is the left side of the embryo, which will eventually form the right and left and cranial caudal side of the developing embryo. What is gastrulation then? Cells from the primitive streak move inward to the ventral surface at the roof of the yolk sac and displace the hypoblastic cells from the embryonic endoderm. Now remember this, all the three layers, the ectoderm, mesoderm, endoderm, are found with epiblast. It's just that migration of these cells leads to formation of this layer, and once hypoblast layer is there, they displace the layers, the cells of the hypoblast, to form the endoderm. But hypoblast does not play any role in the formation of gastrulation or trilaminar germ disc formation. The cells of the epiblast remain and form the embryonic ectoderm. I've just told you why it is called the embryonic ectoderm, because this was the same epiblastic and hypoblastic layer which was formed from inner cell mass, which was derived from which will be decided, that I told you previous lecture, that in all those inner cell mass will form the embryo proper. That means all the three germ layers, ectoderm, mesoderm, and endoderm, are actually from the epiblastic cells. They are derived from epiblast, not from the hypoblast. Gastrulation. Embryonic disc from the forms bilaminar discs develops into trilaminar discs. The embryo is now called a gastrulation. We discussed this. Now at different stages, different name is given actually to make it more easy to understand. And when it was initially a zygote, it developed into 2-cell and 4-cell stage, then it became a morula. Morula was nothing but a 16-cell stage. The cell started to divide and continue to increase in size, eventually resulting in a blastula, in which a blastocystic cavity appears. By the time of this blastocystic cavity has gone from the first week of development and implantation into the second week of development, and then the layers have from bilaminar germ disc formed, and now the trilaminar germ disc. Once trilaminar germ disc has occurred, we give it another name. From blastula we give it a gastrula. Each layer of the trilaminar develops into specific tissues and organs. Now, what does ectoderm give rise to, mesoderm, endoderm give rise to? I will be discussing in detail in the next lecture. But just a glimpse of it here. Embryonic ectoderm gives rise to epidermis, nervous tissue, and other peripheral nervous system. Embryonic mesoderm, which gives to smooth muscle cords, connective tissue and vessels, blood cells and bone marrow, skeleton, striated muscles, reproductive and excretory organs. And I will be discussing what are formed from the paraxial, like excretory organs are formed intermediate mesoderm, and what give rise to endothelial tissue is given rise from the lateral plate mesoderm. Embryonic endoderm, epithelial linings of the respiratory tract and GI tracts and glandular cells are found from the embryonic endoderm. Primitive streak forms the embryonic mesoderm up to 4 weeks of the embryo. After the formation of mesoderm diminishes and ultimately regresses completely. Sometimes the primitive streak persists and results in a congenital anomaly called a sacrococcygeal teratoma. Now, to understand this formula, it has to be initially there is only a streak of cells. Why it is called streak? That cells are aligned in such a way that appear on as like a streak, but gradually cells divide to form a groove. Eventually, this all has to form a notochord lumen and notochordal canal. But if this eventually this does not occur, at any point of time this primitive streaks remains open or mesenchymal tissue is not regressed, this may result into sacrococcygeal teratoma. This is the diagram of sacrococcygeal teratoma. Now you must be thinking why it is only in the coccygeal region. Remember, I told you that primitive streak forms the caudal 1/3 of the embryo. And caudal one third would mean mainly the limbs and the sacrococcygeal area. So this results in sacrococcygeal teratoma. We have covered up till now the gastrulation or formation of trilaminar germ discs, formation of primitive streak, and how actually that was the epiblast cell migration have given rise to 3 cell layers now, which is on the outermost or uppermost is the ectoderm. In the middle, it is the mesoderm, which is further divided into 3, which is the paraxial mesoderm, intermediate mesoderm, and lateral plate mesoderm. And then the lowermost becomes the endoderm. We have also discussed formation of primitive streak, how initially primitive pit is formed, and then from cell starts to migrate to appear as a streak. From primitive streak, primitive groove is formed, and what is the role of primitive node, and how does this results in establishment of axis. Now we will be discussing formation of notochord, formation of primary secondary villi and definitive placental villus, formation of Allantois and congenital anomalies during 3rd week of development. Coming to the development of notochord. The mesenchymal cells from the primitive pit and primitive node migrate cranially in the middle between the epiblast and hypoblast until these cells reach up the precaudal plate. To look at this, they have to go back to the diagram. I told you there will be a primitive node. What are these actually primitive node? These are epiblastic cells. They migrated so much that they appear as a bump or a node-like structure. From this is the point from which the cells will continue to migrate from caudal towards the cranial end. And as they continue to migrate, there is also formation of groove-like structure because they initially appear as streak, but then again divide and become so much that they appear like a groove. And eventually this groove has to come close together to form a tube-like structure. Precaudal plate, a small circular area of the columnar endodermal cells, where the ectoderm and endoderm are in contact. Precaudal plate is the primordium oropharyngeal membrane which leads to the oral cavity. The cells constantly migrating from the primitive streak and node to form a solid cord of notochordal process, which soon acquires a lumen called as notochordal canal. Now remember, this is actually cells are not only migrating, if you see it in a 3D, they would be migrating in 2 axes. They will be migrating in from cranial to caudal axis, from caudal to cranial axis, and from dorsal to ventral axis. That is, they are going from caudal end towards the cranial end as well as they are going down. So if you see this, that a cell is going like this and then going down like this, the end result is a 3D structure which is called as notochordal canal. So this is another diagram. If you appreciate this diagram and you take a cut section at this level, cutting it horizontally or transversely at this level, it would appear like this. Now this is the primitive groove. This is the cranial end which is forming the oropharyngeal membrane. And the cells are migrating in 2 ways. Now they are going towards this as well as they are going downwards as well. So then and the cell's migration takes in 2 planes. This results in a tube-like structure. which can be appreciated here that notochordal plate has resulted in the formation of notochordal cord or notochordal lumen-like structure, and mesoderm comes to lie on the sides of it. As now this is the ectoderm, it was the mesoepiplastic layer which has started migrating. It migrated in two planes, that is towards cranially, as well as it went from dorsal to ventral area and it migrated inwards. As a result, mesoderm came to lie towards this notochord in between, and this is the endodermal layer. You can appreciate this is the just part of the mesoderm which is lying adjacent to the notochord is termed as paraxial mesoderm. And then there is intermediate mesoderm, and this is the lateral plate mesoderm. Now, all three parts of the mesoderm will give rise to different structure, which I will be discussing in the next lecture. But at this moment, if you appreciate, notochord formation has taken place. The notochordal process elongates by invagination of cells from the primitive pit. The primitive pit extends into the notochordal process, forming a notochordal canal. The notochordal process is now a cellular tube that extends cranially from the primitive node to the precaudal plate. The floor of the notochordal fuses with the underlying embryonic endoderm. As I told you, to understand how this actually cells have enveloped each other to form a tube-like structure is that they are migrating towards the cranial pole as well as dorsal to the ventral area. So when they dive down as well as migrate forwardly, this results in a tube-like structure. This is another diagram which actually showing the cut section at different levels, which is at 17 days and 19 days during the third week. So this is how it appears on the dorsal view at 17 days. And this is the primitive node, this is the primitive streak, and it is trying to progress. The cells of the epiblast are actually migrating cranially as well as they're going down ventrally. But we won't be able to see it on this view because it's from the top or a dorsal view. If you see this diagram, now this is showing how this neuroplate formation is. Eventually these cells gonna be first forming the notochordal plate, then notochordal tube, and this notochordal tube will help in formation of neural groove or neuroplate formation, which we'll be discussing in the next lecture. Now this is the surface ectodermal cells. As they have started to dive down, you can appreciate right over here. At this point, this is the amniotic cavity, this is the ectodermal cells, notochord, and this is the mesoderm. If you see it on the transverse section, and this becomes the endoderm. Gradually, as now they have increased in this, on dorsal view, it appears to have, from the process of neurulation have started actually, and this neural groove has started to unite. But if you appreciate on the transverse section, you have a neural groove. This is the notochord, and this is the mesoderm, and this is the ectoderm. Formation of notochordal plate. The fused layer gradually undergo degeneration, resulting in formation of openings in the floor of the notochordal processes, which brings the notochordal canal into communication with the umbilical vessels. The openings rapidly become confluent and floor of the notochordal canal disappears. The remains of the notochordal processes from the flattened groove is called as the notochordal plate. Beginning at the cranial end of the embryo, the notochordal cells proliferate and notochordal plate infolds to form a notochord. The proximal part of the notochordal canal persists temporarily as a neuroenteric canal, which forms a transitory communication between the amniotic and umbilical vessels. When development of the notochord is complete, the neuroenteric canal normally obliterates. So this is important. Again, to understand a very basic thing is that first there is a streak formation, then from streak it becomes a primitive groove. The cells are migrating in such a way that they appear to be a groove-like structure. Gradually, this groove is such that it's going down and going forward. Eventually, the cells come to unite to form a notochord, but these notochordal cells which are lying at the floor, they starts to disappear to form from groove notochordal canal, it becomes a notochordal plate. Once the notochordal plate is formed, there is a temporarily opening between neuroenteric canal and the primordial vesicles, but gradually that also obliterates, because now this notochordal plate will give rise to formation of a new thing which is called as notochordal plate will give rise to for neurulation. Now neurulation will be discussed in the next lecture. But how all this process is actually carried out and what are the signaling pathways, although it's not very much completely understood. But in case of a notochord, the inducer is the signals from the primitive streak region. Induce a notochordal precursor cells to form a notochord, a cellular rod-like structure. The molecular mechanism that induces these cells involves at least SH signaling pathway. This is a type of genes which are involved in this from the floor plate of the neural tube. But exactly how this is actually started by the primitive streak cells is still unknown. But it's speculated that mostly it is the SHH pathways involved. Functions of the notochord. It defines the primordial longitudinal axis of the embryo and gives it some rigidity. Provides signals that are necessary for the development of axiomusculoskeletal structures in CNS. Contributes to intervertebral discs. In adults, it persists as nuclear pulposus. If you see an adult vertebra, you have one vertebra up top and below, in between you have a nucleus pulposus, which is actually which provides a cushioning effect during the movements of one vertebra over the other. So in adults, the nucleus pulposus is actually the remnant of notochord in embryo. Now coming to the Allantois. It appears on day 16 as a sausage-like outpouching from the caudal end of the yolk sac into the connecting stalk. It is involved in mammals with early blood formation and associated with urinary bladder development. But in humans, this excretory organs and bladder and all these kidneys are actually not formed from the Allantois, rather from the intermediate mesoderm. It becomes obliterated in humans and becomes urachus and remains a medial umbilical ligament. From once this will persist in adults as a medial umbilical ligament. Now this is the diagram which is showing, as you can appreciate, this is the caudal region now. This is the, it is embryogenesis has taken place, limb buds have appeared by this time, and this is the yolk sac, the means of the yolk sac now which has regressed. The uteroplacental circulation has been developed. Now this is the Allantois. This will later on form the urachus and eventually in adults will be only part of the median umbilical ligament. Now we will be coming to how, when all this process is going on, cells are continuously dividing, they need a lot of nutrients and oxygen. From where all these nutrients and oxygen is coming through? Now that is provided initially by the diffusion, which I told you, when the sensitive trophoblast invaginates into the endometrium, they results in the lysis of the cells and spaces are created. In those spaces eventually later on become blood filled, and then the nutrients and oxygen diffuse through these layers. But as embryo grows, it's not possible for all the nutrients, it needs to be achieved through diffusion. So there has to be a mechanism or establishment of uteroplacental circulation. So to start the process, there is initially formation of primary villi, that's secondary and tertiary villi, and eventually this results in formation of uteroplacental circulation. At third week, the trophoblastic cell consists of cytotrophoblast at core surrounded by sensitive trophoblast. This marks the formation of primary villus as sensitive trophoblast penetrates the decidua. During the further development, the mesodermal cell penetrate the core of the primary villi and start forming the secondary villus. The end of the third week, mesodermal cells in the core of the villus begin to differentiate into the blood cells and small blood vessel forming the villus capillary system. This villus is now known as tertiary villus. Now this, after formation of tertiary villus, this will result in formation of uteroplacental circulation. This is the diagram which explains the formation of Allantois. As you can now appreciate that the embryogenesis is taking place, the limb buds have appeared, the upper limb buds and lower limb buds are there. Now this is the yolk sac, with the secondary yolk sac now regressed. This eventually will form the urachus and eventually persist in adults as a median umbilical ligament. Now we know by this time the cells are actually continuously dividing, and from where this nutrients and oxygen is coming. We initially knew that there were two layers of cells in situ trophoblasts and cytotrophoblasts. Initially, the in situ trophoblasts penetrated into the endometrium. There was a lysis of the cell resulting in dead spaces, which were eventually blood filled. This blood filled, the nutrients and oxygen diffused from those layers, blood pools or blood islands into the embryo. But as embryo is growing, the demand of oxygen and nutrients is getting more and more. So all this cannot be met by simply diffusion. So then it has to, a proper uteroplacental circulation has to establish. This starts with initially formation of primary villi, which leads to formation of secondary villi and then tertiary villi. At third week of the trophoblastic cells consist of cytotrophoblast and cytotrophoblast. This marks the formation of primary villus as syncytial trophoblast penetrates the deciduum. During further development, mesenchymal cell penetrate the core of the primary villi, forming the start of the secondary villus. The end of the third week and mesodermal cells in the core of the villus begin to differentiate into the blood cells and small blood vessels, forming villus capillary system. This villus is known as tertiary villus, and this marks the start of the definite placental villus or formation of uteroplacental circulation. This is the diagram which is actually showing how the mature villi have formed. Now this is the sensitive trophoblast and this is the endometrium. It starts to invaginate. Eventually the primary villus forms, then secondary and the tertiary villi will be formed in this formation. Now this is showing establishment of uteroplacental circulation. As we know that there were two layers of trophoblast. In the second week it divided into sensitive and cytotrophoblast. Cytotrophoblast was only surrounding the inner cell mass, while sensitive trophoblast penetrated and invaginated into the endometrium. As now in the diagram B, you can appreciate the sensitive trophoblast invaginating into this, resulting in a mesodermal core formation. Eventually, the villi starts to appear once the blood capillaries form. This becomes a tertiary villus. By this time, it's only diffusion. By this time, there are primary villi. They are actually the nutrients and oxygen diffused from these blood islands into the primary villi and then to the embryo. But once tertiary villus has formed, there are actually small capillaries have been formed so that which can bring the blood from mother's blood to the embryo. This is another diagram which is showing an advanced form. Once the tertiary villus has formed, you can appreciate this, that invagination has taken place so much that this is the capillary formation and tertiary villi can be seen forming in between. So coming to the summary, the most characteristic event during the third week is gastrulation, which begins with the appearance of primitive streak, which is its cephalic end and the primitive node. So gastrulation is actually formation of trilaminar germ disc. That how the epiblast cell starts to migrate and form ectoderm, mesoderm, and endoderm. Epiblast give rise to all the three germ layers in the embryo: ectoderm, mesoderm, and endoderm, and these layers form all the tissues in the organ. Cephalic and caudal ends of the embryo are established by the primitive streak. This also develops the dorsal ventral axis as well as the right and left axis. Primary villus is converted first into secondary, then into tertiary, so that the uteroplacental circulation can be established. This is the lecture outline. We have covered in this lecture is the gastrulation or formation of trilaminar germ disc, formation of primitive streak, and how this primitive streak leads to primitive node formation and primitive groove, and how this migration actually takes towards the from caudal to cephalic end as well as dorsal to ventral area. Formation of notochord, and how these cells actually migrate to form initially the notochordal canal, then they regress to form a notochordal plate, which will be later on needed in the formation of neurulation. Establishment of body axis and interembryonic mesoderm, formation of primary, secondary, and definite placental villus and tertiary villi, formation of Allantois, and congenital anomalies. We discussed sacrococcygeal teratoma, which is one of the anomaly if notochordal plate persists or notochordal canal does not regresses completely and a lumen persists. This results in a sacrococcygeal teratoma. For more videos and for more information, keep watching sqadia.com. Thank you.